Welcome to iCanX. I'm Paul Weiss, one of our hosts, coming to you from UCLA. And it's my very great pleasure today to host Paolo Samorì.
Hi.
Professor Paolo Samorì is Distinguished Professor at the Université de Strasbourg, Director of the Institut de Sciences d'Énergie Supramoléculaire, ISIS, but not that ISIS, and Director of the Nanochemistry Laboratory. He's a Fellow of the Royal Society of Chemistry, the European Academy of Sciences, Academia Europa, the Royal Flemish Academy of Belgium for Science and the Arts, the MRS, and the University of Strasbourg Institute for Advanced Study. He's won many, many prizes. His research focuses on nanochemistry, supramolecular science, materials chemistry, and scanning probe microscopies of graphene and other 2D materials and functional, organic, polymeric, and hybrid nanomaterials for applications in optoelectronics, energy, and sensing. And our theme all of this month will be applications of nanoscience. So it's my great pleasure to introduce my friend and colleague, Professor Paolo Samorì. Paolo, the floor is yours.
Thank you very, very much, Paul, for the kind introduction. Thanks to Alicia and Paul for the invitation. It's a great honor and great pleasure to be here today. What I'm going to do during the next 60 minutes or so is to try to convince you that molecules are a great enabler when they combine with 2D materials. So we are molecular scientists by training, and we entered in the world of 2D materials, let's say 10 years ago. And we started really trying to modulate properties of 2D materials with molecules. This is what we do in Strasbourg. Now, the activity of my lab is rather broad. Actually, we use a variety of materials. Can be organic and polymeric, can be molecular switches, can be 2D materials, can be even inorganic nanoparticles. But this is not what we are interested in. We are interested in developing functions. And so we try to combine indeed this kind of, let's say, classes of materials, making a hybrid, making interfacing them, making blends, doing chemical functionalization in order to adjust properties. We do all the multiscale characterization that is required to understand as much as possible. And then we develop proof of concept applications that are going in different directions. We do quite a lot on optoelectronics, you will see today. We work a bit also on energy storage and conversion. We start playing with water purification. We enjoy very much playing with chemical sensing and physical sensing, and also recently we play with cement and civil engineering. So we try to develop a simple concept also to tackle the problem that our society has to tackle. So today, actually, we will focus mostly on 2D materials, and of course, there is a wide variety of 2D materials you can choose or that are already available. They all have some common features, like, as you know, the atomic thickness, a flat surface, a very high surface to volume ratio, and outstanding physical chemical properties. And there is quite a wide diversity in terms of atomic composition and structures. Of course, are well-known established family, like the graphene one, like the dichalcogenides, that will be the focus of today, the 2D oxides. So in principle, one can think of being able to exfoliate over 3,000 layered structures. Now, this has not been done, so there is quite a lot of room for the future. What we are interested, as I said, is not really the materials itself, but the property where we can assess. And of course, you can see that if we just take one property like the electrical properties, we already have in front of us the cases of semi-metal, semiconductor, insulator, depending on the type of material we choose. And of course, also the way it interacts with light is completely different. Now, what makes these materials interesting beside the optoelectronic properties are the mechanical, the thermal, and many other properties that make us hope that there will be some disruptive technologies that can come up soon in different, let's say, field of science and technology, going from security to touchscreen to communication and automotive and so on and so forth. Now, the first thing that you have to consider when you deal with 2D materials is that you need to have them available. And so there are a number of approaches that have been developed in order to produce 2D materials. Let's say, I think this plot, there was a report in a recent review, is quite interesting because it shows clearly that there is a kind of parameter that has to be taken into account, which includes the, let's say, the production cost and the production yield, but also the type of material that is produced. And so the precision in the production, the number of defects that you might have, the size of the material. And so these are all parameters that are actually hard to be displayed in a 2D graph. Here, actually, you can see the two extremes. The two extremes are on the bottom right. You can make a mechanical exfoliation with the pioneering approach, the one of the Scotch tape that was developed by Andrei Gaim and Kostya Novoselov. And you make very tiny flakes, but with outstanding electrical properties. You can use more sophisticated chemical approaches, starting from well-designed molecular building block and tethering them covalently to create, for example, well-defined nanostructure like nanoribbons. You can use more established approaches like CVD, or you can think of having approaches that have a high throughput and a very low cost that can be the one that are associated to solution processing. So you make inks. Inks can actually be done in different manners. These are just a few examples. The most, they say the pioneering approach based on inks was the one that was developed by Johnny Coleman in 2008, which is the one using ultrasound as a mean in order to exfoliate. That means to break the strong interaction that are holding together the adjacent flakes. And but you can also, over the years, I mean, other approaches have been developed. For example, high shear mixing exfoliation, also done, pioneered by Johnny Coleman. There is electrochemical exfoliation, where there was for sure a key players were Klaus Muren and Xilian Fang. And there are many other approaches that have been developed over the years that can be considered in order to produce some functional inks. Now, overall, as I said, the challenge is the one of providing energy to the system such that you break the strong interaction that you have between different layers. Now, this kind of breaking can be done by making use of a specific solvent in addition to the, let's say, to the physical mean that you might use, like the sonication. For example, NMP is an ideal solvent for breaking this kind of interaction in graphene. But actually, it can be assisted and boosted, this kind of, let's say, breaking of interaction using some molecule that act as surfactant. And so here is already the first example of how molecule can be, let's say, instrumental in the field of 2D materials. So just for the making of the 2D material and for the high yield exfoliation. Now, of course, when you deal with a molecule is not an innocent mean. A molecule is has some intrinsic function, and therefore, once you combine also during the production the 2D materials with the molecule will play a role in terms of the overall physical properties of the hybrid. So it's a way to create functional ink. It's a way to create nanocomposites, and actually is an approach that is upscalable to the point that, for example, you can make several tenths of liter, and there are a number of companies that are actually focusing, they're making their business out of this. Now, let's focus today on transition metal dichalcogenides, and the reason, of course, is because they are the prototypical 2D semiconductors, and so they can be interesting for the next generation of electronics. But of course, there are a number of things that still have to be tackled, some problem that has to be solved, and something that has to be improved. Now, the first aspect that for sure needs to be improved is the fact that there are a number of N-type, let's say, semiconductor based on 2D transition metal dichalcogenides that are available. There is a scarcity of ambipolar and even stronger scarcity of p-type. So that is one of the things in the to-do list. There is a lot that one can do by playing with defects. So defect engineering, for sure, is a tool to modulate properties, to modulate charge transport, and also to allow functionalization. The functionalization is key and can be done in different manner. with molecule in order to control doping. And actually, finally, also to boost the charge transfer, charge induction characteristics. So these 4 points in green are those that somehow will be at the core of my lecture of today. But of course, the challenges are not only these 4, there are a number of other challenges. For example, the ability to be able to control the formation of semiconducting structures rather than quasi-metallic phases. Of course, the ability of making larger and larger film for large area application, large area electronic, of course, the film has to be crystalline, and a certain point cost will be an issue. Of course, the starting materials, graphene is rather cheap, and when you start moving from graphene to TMDC, there is a huge increase in the cost of the starting material, and also processing cost is something one has to always try to lower. So I think this is in the agenda of everyone working on TMDCs for electronic in particular. Now, let's see what we have been doing in my lab, and here we start our contribution to this big field of science and technology. Recently, by trying to tackle actually the first point that was here on the list, the one of the scarcity of the p-type derivatives, Antonio, that is an outstanding postdoc in the group, he came and proposed to develop a new allotrope of phosphorus, that is violet phosphorus. Violet phosphorus was recently reported, recently synthesized in 2 papers that are listed here. It's interesting because, first of all, it has a direct band gap. This is something you can find also in black phosphorus, over which you can find thousands of papers in the literature. But the peculiarity of violet phosphorus is predicted to be a p-type. In principle, the isolated flake, the single layer is theoretically is expected to have a mobility that goes from 3,000 to 7,000, so it's pretty high. Typically, it is produced as a byproduct of when black phosphorus is produced, but one has to be reminded that it's much more stable than black phosphorus, and therefore there is a simple way to make it. That is when you crystallize, when you heat it up, you arrive at a certain temperature where the black phosphorus actually is completely destroyed, and you have a window of 50 degrees in which you can produce pure violet phosphorus. So this is what we have been doing by combining this essentially with tin and tin iodide as transport agents. And this way, we could actually control the nucleation process and avoid the formation of black phosphorus. Once we have created this kind of crystal with the size on the centimeters scale, we have exfoliated this in DMF. And you can see here the flakes by electron microscopy and by AFM. The lateral size of the flakes can go up to 2 micrometers in size, and the thickness, the average thickness is about 8 nanometers, so a few flakes thick. And now we made films out of it. We made the transistors, which showed in the film a mobility of over 2 centimeters squared per volt per second. This is one order of magnitude higher than the typical p-type derivatives. There are a number of selenium one that are available. So the mobility in an optimized device is not bad at all. Of course, we are targeting to study the mobility of isolated flakes and see how far we go. And actually, as a proof of concept, and try to make use of the fact that we have developed a p-type, we fabricated a CMOS type of device, and by combining an n-type that is the MOS2 and the violet phosphorus p-type, and we also have a voltage gain that is as high as 17. So that was the first proof that, let's say, violet phosphorus can be used for electronics. And I think it really demonstrated that there are a number of potential new materials that can be created. And here as well, we need the creativity of chemists to try to develop new materials using a typical type of composition. Oops. So of course, you can make new materials, but after all, the choice of the materials gives a limited properties tunability. And here is where the combination with molecule come into play. And the idea is that we want to combine indeed the 2D materials molecular science, because we find it to be a way to tune and improve the physical properties of 2D materials, and also to be a way to confer new properties to the materials and to go towards the development of multifunctional materials and devices. Now, the interaction between molecules and 2D materials can be of different type. Of course, there are the two extremes. That is, let's say, the strong interaction via covalent forces, so the chemisorption, or the weak interaction that can be through weak interaction, non-covalent forces that can be defined as physisorption. And we label in our lab that this kind of functionalization at speed is simple, programmable, effective, enduring, and diverse. And if you want to go a bit more in detail, you can see that there is a whole variety of strengths in the interaction. It goes from very weak interaction to very strong interaction. This can be done on continuous film and also on isolated molecules. So continuous film, you can start from the very left, where by van der Waals interaction, you can see that linear chains can interact with the 2D materials of different type, including KMDC. You can have dipolar interaction if you have molecules that exhibit a dipole moment. You can have the charge transfer processes. You can have defect healing. This is already some kind of covalent interaction. You can have the covalent functionalization of the 2D materials. And now, therefore, essentially, if you want to combine the 2D materials molecule interacting with 2D materials, what you need is that molecule by design, they exhibit an anchoring group that is here in blue. And this anchoring group will interact at the covalent or non-covalent level with the 2D sheets. And then the molecule by design will also have a red, let's say, moiety, and this red moiety is the one that will be used to confer functions. So if you assemble this kind of functionalized flakes, for example, you can functionalize this in the ink. You assemble them, and you can create actually some, let's say, functionalized inks or functional coatings, and this can be interesting, for example, for application in wearable electronics in multi-responsive coating and sensing. But you can actually use also molecules that display two anchoring groups. And this way you can tether covalently from the two sides the molecule to a different flake. And this way you can create foams that they have high porosity. And of course, high porosity can be interesting for energy application. They can be interesting for catalysis, can be interesting for desalination, can be interesting for sensing. So again, here you just need to use the creativity that the chemist can have to decide which are the anchoring group and which are the functions you want to, let's say, integrate in this porous structure. Now, as I said, we are focusing today mostly on optoelectronics. And so I like to target as field effect transistor, like the basic element for electronic application. And I'll try to be very fundamental in my approach. And so, of course, when you deal with whatever field effect transistor and whatever semiconductor, can be a 2D material, but can even be an organic semiconductor. In organic semiconductor, there are very basic processes that one has to consider and optimize. There is a charge injection between the electrodes and the semiconductor, and the extraction as well. There's a charge transfer within the semiconducting materials, and there is a gate modulation. So these are all processes that we try to tackle one by one with our approaches, combining molecules to the materials. And so the first thing that we focus on is the charge transport. And we have to bear in mind that any kind of 2D materials you will deal with, even the most perfect one, is defective rich. And so being defective rich, of course, defects frequently have a bad connotation, but I will try to convince you, I hope I will be able to convince you, that defects are not all negative. And there is a number of things that you can do with defects that you need to exploit. So this kind of approach started when Simone Bertolazzi was postdoc in our group quite a few years ago. And he came with a strong background in TMDC, with the PhD thesis done with Andras Kiss in PFL. And so we decided we need to focus on MOS2. It can be CVD, can be Scotch tape. And we decided to play with defect engineering. And the idea was pretty simple, that any kind of MOS2, for example, from CVD, you have every 10 by 10 nanometer, you have a sulfur vacancy. And so, of course, the sulfur vacancies is a charge scattering center. So it's something that you don't really want to have if you want to do fast electronics. If you actually like defects instead, you can generate defect easily. And the easiest approach is the one of you get the argon beam of an XPS and you irradiate your sample. And so you can see here that actually upon irradiation, we are creating more and more defect. And so we are lowering the electrical characteristic of our single flake. You can see how the mobility decreased drastically with the upon irradiation. Now, of course, there is always a way to solve problems, and this is the one of healing defects. And defects can be healed by, for example, here having thiolated molecule interacting with MOS2 in order to fill the vacancy that was previously created. Now, this is very interesting because, first of all, you can recover the electrical characteristic that you can see from this electrical plot. But on the same time, it gives you a lot of room for the grafting of different type of molecule to the basal plane of disulfide. Now, of course, the thiolated molecule is something that you can easily find on the market, or you just follow the literature of our chairman, who has been playing with thiolated molecule with gold. In fact, the interaction between thiols and gold have been such that in the Aldrich catalog now you can find a couple of thousand of thiolated molecules. So you have the broadest variety of molecules you can choose from the market. Now, so this was the starting point. And then what happened is frequently science continues also after the working hours. And I was in Dresden, invited by Jan Feng at the conference. And at the bar, I met Johnny Coleman. And in front of a beer, I tried to ask him a nasty question because he was just publishing this paper in Science in 2017. That was all about a printed MOS2 transistor. And actually, I was arguing with the fact that the field effect mobility that he reported were not very high. And actually, I was asking him the reason why. And actually, the problem that he brought immediately to my attention was the fact that he has a serious problem with the interflake electronic conductivity. So essentially, you needed to find a way to generate percolation pathway for charge, for the charges to be transported throughout the film. And at that point, I have an outstanding PhD student, Stephanie Polk, that was just starting the PhD in my lab. So what I decided to do is to take advantage of what we had just reported with Simone Bertolazzi and go one step further. Essentially, when you exfoliate 2D materials as a ink, you create flakes that are isolated and dispersed. And therefore, at that point, the goal is somehow to find a way to bridge this kind of flakes with the, let's say, the right piece of the puzzles. And so, in other words, you have these flakes of, for example, MOS2 or tungsten disulfide or rhenium disulfide, and you combine this with the doubly thiolated molecule that acts as a bridge. Now, this molecule indeed has the two thiols in the para position and a conjugated bridge that can be used for charge transport. And so the goal is actually that on the same time, we use the thiol unit to yield the sulfur vacancies in the transition metal dichalcogenites, and we use the conjugated nature, electronic nature of the molecule as in order to covalently electronically bridge the adjacent flakes. So the way we produce the film was, the networks actually is very simple. We start with the ink and we drop cast the ink in between into the digitated electrodes. Then we put this in the nitrogen atmosphere and we apply a drop of the doubly thiolated molecule in hexane. So what is important is that, as everyone knows, the thiolated molecule tend to form disulfide, and therefore this kind of oxidative coupling has to be avoided and can be avoided by working under nitrogen and under dark. The other requirement that one has to try to always bear in mind is that solvent molecule, as I will show you in a few minutes, they are not innocent. So frequently they are dopant, and therefore you have to try to use the most apolar solvent as possible. So here we decided to play with hexane. And so the result is what? The result is, well, the cartoon is the following, that the idea is that this kind of molecule which bridge adjacent flakes, creating percolation pathways for charge transport. Now, let me prove that this was really happening. One piece of evidence is we got from the X-ray photoelectron spectroscopy measurements. And actually, on the left, I always place the films which consists of flakes that are disconnected. And on the right, I have the network where the flakes are covalently connected. You will see actually that upon benzene dithiol treatment, we have a reduction of this kind of stoichiometric, substoichiometric component, this flat band here. And so there is a reduction of the sulfur vacancy from 5% to 0.5%. So this is the first piece of evidence. The second piece of evidence we have comes from the Raman, that actually here we focus our attention on the full width of maximum of the A1-2G and the A1G peak, which we showed to narrow down on 10% upon the network formation. And also the ratio between them shows an increase. So actually all this is something that can be, let's say, explained in view of the reduction of defect density, in particular, the fact that we have less edge-terminated structure. Indeed, most of the defects are on the edges, and most of the connections done with the molecule occurs at the edges of the flakes. Now, we also noticed that the difference between the film and the network was hydrophilicity. So the film was very hydrophilic and the network was very hydrophobic. And actually this hydrophobicity was such they gave a much stronger, let's say, stability or robustness of the network underwater. So with no detachment. And so this, of course, is very interesting for water-based application. Actually, of course, we are interested also to explore the electrical properties when integrated inside a real device. So we fabricate a liquid gate TFT, and we decide to use this kind of geometry because the dielectric liquid, which penetrates the free volume of the semiconductive films, allows to have a good volumetric gating. Now, without making the long story, to make the long story short, the performance are such that upon network formation, we have an increase of the field effect mobility of 10-fold. We have an increase of the ion-IF ratio of 10-fold. Threshold voltage is not changing, and this means that we are not doping our system. And actually, we also serve the device which is much faster in the case of the network. So there is quite some, let's say, exciting thing that one can do in the future here, and it's essentially all about starting from 2D, making a covalent network of 2D flakes, going to 3D. And of course, what one can do is to choose different type of materials to do that. Of course, this will require a different type of chemistry in order to have the covalent grafting. And of course, also one has to be a bit creative in the bridge that one uses. It can go well beyond the one of a simple phenyl and use this to introduce some functions. So I leave, let's say I remain very general, but I leave it to the chemical creativity of the audience to exploit this. Now let's go back to the fundamental process that we have in field effect transistors. And now, in a bottom gate, bottom contact, of course, we have to deal with the problem of the charge injection and charge extraction, which needs to be optimized. And frequently, a way to do that in order to optimize the work function, so the relative energetics of the electrode with the one of the semiconductor, is based on the when a metallic electrode like gold is employed. One uses the thiolated molecule with, let's say, different type of add group that can be R1 or R2, can be actually also functionalized in an asymmetric fashion on the source and drain electrode in order to optimize the injection and extraction. Now, this is something that has been demonstrated for the case of bottom contact, bottom gate transistor, but is something that actually would be more interesting to be applied for top contacts instead of bottom contact, because of course the top contact has the advantage of having a much wider area of injection. So this is what I'm going to show you now, a recent work that just appeared in the literature that was done by Bill Hahn in my group, in which he was able to fabricate asymmetrically functionalized top contacts for field effect transistor based on MOS2. Now, the idea was that he first created this kind of small gold, let's say, flakes, and he has, using a mask, this kind of patterns of gold has been let's say, functionalized with different type of thiolated molecule, can be doped that is such that is used in order to lower the work function from 5 to 4.3, or can be a fluorinated derivatives, which indeed is used in order to increase the work function up to 5.6. And then he was able to perform a dry transfer process and turn it upside down, essentially, on a device in which we use cytop covering the silicon dioxide, and we chose this because of its low surface energy and the near free trap states and actually absence of dangling bond. Then, of course, we placed on the top the molybdenum disulfide, and it transferred the asymmetric electrons. Now, this allowed us to optimize the charge induction at the interface between the electrodes and the semiconductor by minimizing the injection barrier. In particular, in the case we choose the doped devices, the doped functionalized electrodes. And this allowed us to reach a mobility of over 30 for an optimized device. Now, of course, then one can think about doing something different and something more sophisticated. For example, in this asymmetric functionalization, we could fabricate Schottky diodes. And in this case, we showed that we have a rectification ratio that can go up to 10 to the power 3. So I think here there is a lot of things that one can do in the future by exploiting this kind of asymmetric functionalization of top contacts. And again, is really a fundamental building block for doing electronics, eventually by exploring how light can interact with matter in this kind of unique geometry. Now, the next, of course, the next challenge that one has to take care of in the case of semiconductor is the one of tuning the properties, in particular in this case of 2D materials via doping. There are a number of approaches for doping 2D materials that have been reported in the literature, which are actually belong more typically to, let's say, to approaches that are used by the physics community, like substitutional doping, ion intercalation, or electrostatic doping. Now, the approach we will pursue is the one essentially of fabricating hybrid van der Waals heterostructure, and namely to have the 2D materials and grow on its surface, let's say, another layer that actually can be a molecular layer. So here is not too different from the approach of the classical van der Waals heterostructure. So we try to combine 2D materials with layers that are molecular based. And so this is nothing else than the approach of, let's say, that you can have in the kitchen. So you take a layer structure that can be the one of an hamburger, and you intercalate another layer that can be our functional molecule that is used in order to alter the properties. The properties can be the taste, or can be, for example, the electrical properties. And of course, the more you fabricate sophisticated structure, the more the taste can be, let's say, sophisticated and interesting. So indeed, the approach of the van der Waals heterostructure was already introduced nearly 10 years ago. There is a very nice, let's say, perspective article that was reported in Nature in 2013 by Andre Geim that showed that how you can nicely modulate and diversify properties to the materials in terms of electrical, optical, and magnetic properties by overlapping physically a different type of 2D materials and also rotating one on top of each other in order to make 2D periodic potential. Now, the first limitation that one can see here is let's say, the choice of the material one can go for, and also that if one doesn't play too much by tearing one material on the top of the other one, it's pretty hard to go from the 2D periodic potential to other type of dimensionalities. Now, that was the approach of the physicists, just to physically overlap 2D materials. The chemists actually will think in a slightly different way. That is the one of taking any type of 2D materials and literally deposit or throw on its surface any kind of molecule that can be electron donating or electron withdrawing. Now, here I like to just to open a very small window and provide the information to the audience that small organic molecules that frequently are used as, let's say, solvent molecules, so that are supposed to be kind of inert from the electronic point of view, are not really inert. And so I warn you to watch out that when you use a small molecule like the one that are listed here, that sounds to you like a very banal and innocent molecule, like chloroform, acetone, benzene, ethanol, hexane. Actually, they do dope to a certain extent to the semiconductor. So in other words, the message that I want to convey here is that as long as you are able to deposit molecule from a gas phase, that's the best way to do it, because then you can forget about any potential interference of the solvent molecule. Instead, if you are forced to do solution processing of the molecule, the surface of the 2D material, then you have to make sure that you do blank experiment and try to have fully under control the effect of the solvent molecule alone. So that was a very nice work done by Yevang that we reported in 2 separate papers a couple of years ago. Now, here, let me now start a new chapter that is the one on doping to the materials with molecule. And what I'm going to focus on is to try to, let's say, consider 2 different types of mechanisms of doping. And also to do that, we're going to use approaches that are reversible. So we can have reversible doping. Now, these are the 2 different types of, let's say, mechanisms I like to focus on for what concerns molecular doping of 2D materials. The first one is the one that is based on the molecular dipole-induced shift in the Ward function, and is what you have when you place a polar molecule on the top of the 2D materials. So here, the electric field that is emanated by the dipole that acts as a local gate, and so it can shift the Ward function of 2D materials, and therefore this induces a doping effect. And actually, what happens is that you are doing nothing else than you're manipulating the charge, the carrier concentration of the 2D materials. Here, I will show you that you can do with light, and you can use light in order to control distribution of dipoles. And in particular, we will try to have a control over the doping effect by by tuning the mutual orientation of dipole unit with respect to normal to the surface. And so overall, you will see that we will try to boost this doping effect by using collective processes. The second approach will be the one of charge transfer that I will explain you later on. So overall, the idea is that we make a hybrid van der Waals heterostructure, and we exploit collective properties in order to have a controlled self-assembly, and then to convert the single molecule isomerization process into the macroscopic change of the electrical characteristic of a 2D material. And so the idea is very simple, that you take a 2D materials and you take the small piece of the Lego that are your molecule, and you assemble them, creating, let's say, highly organized crystalline structures. That can be done with a very simple chemistry that was reported already about 30 years ago. You take alkanes that are the simplest molecule possible, and you will see that alkanes, they love the basal plane of MOS2, they love the basal plane of graphene, and they form crystalline lamella structures. And so at that point, you can just use this as a template and start functionalizing the alkanes in order to control the positioning of functions. So to decorate your 2D materials with function with an atomic precision. Now, on the, let's say, greater context, if you look this as a big picture, my approach to multifunctionality is the one of integrating multiple materials inside a single device, and each material, each component will bring a new function, will confer a new function to the device. So now here I have number 5 position where I can integrate my, let's say, components. So the biggest challenge from the chemistry point of view is the one of being able to physically locate in the position that I marked the given component, and actually also associated to this one is to choose the right component which brings into play the function that one wants to play with. So you see we can asymmetrically functionalize the source and drain electrode. This is 1 and 2. We have the interface with the dielectrics. This is number 3. We can add the semiconductor. That is the 4th function. And we have the top layer that can bring the 5th function. So now that is where is the biggest challenge that we are facing. Now, of course, you can choose what kind of stimuli you want to have to change the properties of the different components. And of course, any kind of device you fabricate has the advantage that, let's say, solution process material that are soft can have. So you can have flexible device, you can have tunable properties, and so on and so forth. So let's start from the basic field effect transistor that is monofunctional. And so it's like having a remote control with a single button. I will show you how you can add more buttons to the remote control. You can make it bifunctional, you can make it trifunctional. And well, the dream is to make it multifunctional. Now, when I start my independent lab in 2003, actually, we start immediately to play with photochromic switches, which are small molecules that can undergo isomerization from one state to the other as a response to a light stimulus. They can be, for example, irradiation with UV light. Everyone knows the case of the isobenzene that can switch from the E to the Z with UV light and go back thermally, or with visible light. Directly, one can switch between the two states that are thermodynamically stable with UV light from open to close, and from close to open go back with visible light. Or spiro-mero, it can go from the spiro to the mero with UV and go back with visible thermally. Now you see here that on the bottom I marked the properties that are changed in each of them. So for example, the isobenzene, you have a huge change of the contour length between the two states. In the diaryl, you have different changes of the energy levels between the two states. For the spiropyran, you have a major change of the dipole moment. So the idea is to use the photo switching molecules as a gate to translate an incoming light input into a change of the macroscopic material. So the one approach that we have developed quite a few years ago was the one of making physisorb, let's say, monolayers of spiropyran. These are a molecule which exhibit a very long alkyl chain. This R group is a C18 chain. The C18 chain is this line here that templates the formation of this lamella structure, and therefore we position the optically responsive group in well-defined position in the space with an atomic precision. And then on the surface, we can in situ change the state from spiro to the mero of the head group and have a different type of electrostatic interaction of that group with the 2D materials underneath. So this was a work done by Marco Gobbi and Sara Bonacchi. And you can see, first of all, that you can, let's say, trace this kind of isomerization process already in the macroscopic scale by XPS. This is occurring on the monolayer of this molecule that is physisorb on the basal plane of graphite or even CVD graphene. You can see that the monitoring the N1S peak in the X-sphere spectra, you have this neutral form in red when you have to deal with the spiro. You radiate with UV light and you generate this blue peak that is a fingerprint of the positively charged nitrogen that you have in the mero. Upon illumination with visible light, this blue peak vanishes to a great extent, and therefore proving the reversibility of this kind of switch. Now, of course, we are more interested to look into the nanoscale, and you can see that you can monitor by scanning tunneling microscopy in situ in dry films the isomerization from the spiro to the mero and back to the spiro. And actually, we can determine a unit cell that is reversible. And you can see that the molecule are much better resolved in the case of the mero. And actually, this has been demonstrated, the reason why, by David Bergeon in Mons, showing nicely that the head group of the mero packs, let's say, flat onto the basal plane of the graphite or graphene, and whereas the head group of the spiro are more disorderly packed, and this gives some dynamic on the time scale of the STM imaging. Now, of course, we are interested in the electrical characteristics, how much we are able to modulate them upon isomerization of the spiro. You can see here that actually we can have, first of all, an end-doping effect due to the physisorption of the spiro molecule. Upon illumination with UV light, by triggering the isomerization from spiro to mero, we have a further end-doping effect that is fully reversible upon visible light illumination. So this shows that we have an end-doping effect with the carrier concentration change that is as high as 4 times 10 to the power 12. The same effect has been observed also on molybdenum disulfide, but I have no time to go through this. Now, the whole idea here is that if you want to maximize this kind of doping effect, you have to be able to control dipoles and to align all of them in order to take advantage of this collective effect. Now you can, I will be, let's say, quite brief because the time is flying and there are a number of things I'd like to show you. But for example, since a key is the orientation of the dipole in the perpendicular to the basal plane of the surface, you can use a coordination chemistry approach. You can physisorb porphyrin of tungstenine flat on the basal plane of the MOS2, and then you can have the central metal zinc or cobalt that coordinate the pyridine unit, and the pyridine can be functionalized with fluorine atom in a different position, and therefore we can control the orientation of the dipole moment. And this allows us to change from end-doping effect when the fluorine atom is more or less out of plane to the in the p-doping, and the end-doping when it's going back to the plane. So this is the case when we have in the fluorine or atom in the ortho position, or if we use a nitrogen unit. Now, similar approach, but again, the time is flying. It can be done by using a slightly more sophisticated molecule, again, pyridine unit, but holding a pillar that is an azobenzene one. Therefore, in situ, we can change the state of the azobenzene upon isomerization from perpendicular to bent. This is highly reversible, can be also played by using pulses of different duration, and therefore controlling the population of molecule of azobenzene that undergo isomerization. And this allows us to electrically access to different levels for multi-level memory application. Now, let me explain you the charge transfer approach we have been working on, which I think is easier to be applied. So the idea here is the energy level alignment determines the doping, and so we favor the transfer of electrons from the material to the molecule or vice versa. This approach was on the basis of the PhD thesis of Q, which was supervised by Zhao Yu in my group, and the idea was very simple. So we first of all focused on the unipolar 2D materials, and we took tungsten diselenide that in this condition was unipolar, and the initial condition we used was unipolar, and this conduction band is 3.5. Then we chose a diaryletin that such that is LUMO level in the closest state is inside the band gap of the tungsten diselenide, whereas when it is in the open state, it is out of the band gap. Now, what does this mean? When a state is in the band gap, it acts as a trap for the charges of the semiconductor. When it is out of the band gap, the interaction are pure electrostatic. So that's the overall idea, that we fabricated a transistor by exfoliating the tungsten diselenide, a few flakes thick. We transfer this to the silicon dioxide, and we fabricate a backgated device with metal contact. We anneal to get rid of all the possible residue for the patterning, and then we deposit a thin layer of about 5 nanometers thick of diaryletin by spin coating, and then we perform the characterization under nitrogen upon illumination different wavelengths. So if we start, first of all, with the tungsten diselenide, an optimized device, a mobility of 16, we have deposited diaryletin layer in the open state, and this leads to a decrease of 20% of the mobility. At this point, we have illuminated with the UV light to trigger diisomerization from the open to the closest state, and therefore we are creating traps. We are creating traps, and this is such that the electromobility of the tungsten diselenide decrease of 50%. And you can see there is also a mild increase of the threshold voltage. Now, if we irradiate with visible light, we are actually able to go back to the initial state of the diaryletin, so the open state, and we can see that we go back to the initial mobility of about 13, and also the same threshold voltage. Therefore, we have a full reversibility in our photomodulation. Now, we can actually take advantage of the fact that the diaryletin is a very robust photo switch, and actually the two states are thermodynamically stable. So we have a high fatigue resistance. And you can see how we can modulate the current about 60%. We can make cycle without any fatigue. And so then one can just show here a very simple cartoon of how we can assess different levels for a memory application. We start from the case where the diaryletin are in the open state. That is a case of level number 0. We radiate successively for 2, 4, 8, and 16 seconds of UV light to assess to level 1, level 2, level 3, level 4. then we irradiate with visible light, we go back to level 0. And this is fully reversible, reproducible. Of course, retention time is important when you deal with memories. Here I show only for 10 days, but we have another example, dye-related interacting with other semiconductor, and we have over 500 days of retention time. Now, as you know, tungsten selenide can be also bipolar. Actually, this is something you can achieve by varying the thickness of the 2D materials. And here, without going into details, I'd like to show you that we could physisorb on the top of the tungsten selenide, the bipolar one, a blend of two different types of dye-relating that have been designed in such a way that one that is dye-relating number 2 has a HOMO level that can be used to trap and detrap the Hall transport, and the number 1 can be has energy levels such that can be used to trap and detrap the electron transport. So, at the same time, we were able to control and to modulate via light irradiation the two types of transport. You can see the irreversibility here, that the Hall mobility can be modulated of 96%, whereas the electromobility was about 40% with the full reversibility. And actually, the device can also be fabricated on flexible substrate. Now, let me move to the very last part of my presentation, which is aimed at showing you how you can increase the chemical complexity and the functional complexity of 2D materials-based devices by using chemical approaches. And here we are dealing again with asymmetric functionalization, but not of the two electrons, but we asymmetrically functionalize the two different surfaces, the faces of the 2D materials. So in other words, what we do, we use a Janus approach, or we fabricate a Janus structure to harness multifunctionality, because the main concept is that we want to expose the two faces of 2D material to two different local environments. Now, of course, one of the two local environments can be the photoresponsive, so photochromic layer, and the other one, we decided to play with organic ferroelectric insulating materials, and we use a very standard one. This polymer has been already reported in the literature quite thoroughly, and actually it is known that it can be used as, because of this large fatigue free remnant polarization, the short switching time and a good stability. So the idea is that we put as a layer underneath the tungsten selenide, the photochromic layer, and we place on the top the ferroelectric layer. So the ferroelectric layer placed on the top will act as a gate insulator layer, and we will change the surface potential of the interface with the semiconductor by controlling the accumulation depression state of the charges in the device. And so in this way, we also take advantage of the fact that information can be stored in a non-volatile fashion by taking advantage of unique properties of the ferroelectric layer. And here you can see that actually two are the approaches that we have developed. The top part of the device is the same, gold electrode and the ferroelectric polymer and the tungsten diselenide, but underneath we have either a physisorb dye-radiating layer or a chemisorb layer of a spiropyran. Indeed, the spiropyran has been synthesized with a silane unit. The silane unit can chemisorb only silicon dioxide. Now, because of time, I will focus only on the dye-radiating approach. And so, of course, most of you, if not all of you, knows what is ferroelectricity. That is obtained if you have a voltage that is applied that exceeds the coercive field. You have the dipoles of the ferroelectric material that partially align with the electric field, and this results in a permanent polarization even when you remove the electric field that is applied. So in this way, the magnitude of the polarization will depend on the difference between the electric field that you applied and the external electric field that you apply and the coercive field of the chosen material. And so what is interesting that depending on the application of the field that you apply, you can assess to intermediate polarization state. And this is, of course, very interesting for application in multi-level memories. Now, the first thing we did was to integrate a 500 nanometer thick layer of this ferroelectric material, place it on the top of the tungsten diselenide in a capacitor type of devices, and we perform 10 cycles, and we can see that there is absence of any fatigue. Essentially, we are changing from dipole up to dipole down. So then, of course, we have to see whether this kind of two different stimuli can be, let's say, used on the same time. And so, first of all, we were not certain that by placing the dirating as underneath the tungsten SLNI, we could still trigger its isomerization. So that was something that we were very happy to monitor, that we can start from the dirating in the open state, we illuminate with UV light, we can trigger the isomerization from the open to the closed state, and this is accompanied by a reduction of the current through the junction, and which is reversible upon illumination with visible light. Then at that point, we needed also to see whether we could, in our device architecture, being able to electrically switch using the, let's say, the top ferroelectric material. So what we observe is that we can actually assess a different state through applying a voltage to the top gate bias when we exceed the coercive voltage of 60 volt. So we have in the P down state, is marked in red, is that we obtain upon applying a plus 60 volt, we have an increase of the electron current, and this is accompanied by a negative shift of the threshold voltage, whereas when we apply a minus 60 volt, the current decreases drastically. We have modulation of 68% of the current, and this is the case where we have all the P up. Now, at this point, I want to show that we can combine the two orthogonal switching. And so we start, first of all, with the highest current possible, that is obtained when the dirating is in open state, and the dipole are in the P down state in red. And at this point, what we do, we illuminate with UV light in order to create traps out of the dirating. And so we close the dirating from the open to the closed state. And this is accompanied by electron trapping and decreasing the current through the junction. At this point, we can further decrease the current by applying a minus 60 volt. And in this way, the process is further depleted and the electrons in the channel, and we reach the lowest current possible, that is obtained by dirating in the closed state and P up. Then we can irradiate with visible light in order to reopen the dirating, so untrap the photochemical, let's say, trapping. And in this way, we can recover partially the current in the channel. Then we can apply the 60 volt again. You can see that we can go back to the initial state with the highest current possible. So the current modulation is highly reversible, and we can see here that the two stimuli are actually can be used in a simultaneous fashion. So what you can actually do then, you can use fast, let's say, lasers in order that each irradiation is such that you have a finite number of dirating that undergo isomerization from, for example, from the open to the closed state. And so we can assess different level of current. For example, here, without using the nanosecond laser, we can assess 84 different levels, but with the nanosecond laser, we could also, in another experiment, reach 256 levels, that is 8-bit memories. Then, of course, we can challenge our approach towards the number of levels we can assess upon electrical application, so using the ferroelectric gate as a stimuli. You can see here that we can assess to 9 distinct levels in a reproducible fashion. Therefore, if we combine them, in this case, for example, we can have 756 level, and in the case we use the very fast laser, we can arrive to up to 11 and sometimes 12-bit memories. So this is pretty much of a record, and I want to stress that the two systems are highly stable, and therefore we have a retention time that is hundreds of days. Now this I'm on the process to finish up my presentation. I hope that I could convince you that there is a lot of room for using the chemical creativity in order to diversify the functions in 2D materials for electronic application. This is the approach that nowadays is called more than more, you can exploit a different type of stimuli responsive systems. So therefore you can really do a lot of chemistry and responsive chemistry here. Now, if you're interested in this kind of approach, we recently came up with the chemical reviews, and Yuda Zhao, that he has been really leading this kind of writing up, has been done a terrific job to sum up all these ideas. Now, with this, I'd like to acknowledge my sponsors. Our sponsors are mostly coming from Europe through different means, the European Research Council project and different type of other actions, including Graphene Flagship, that is providing a boost in the scientific and technological activities in Europe in the field of 2D materials. And I really, last but not least, I need to acknowledge the amazing group of highly talented chemists, physicists, and engineers that are in my lab. Indeed, I love to have this kind of interdisciplinary enterprise because, first of all, I'm learning a lot from them. And actually, because this allowed us really to have a holistic approach to science that goes from the making one material to the proof of concept. Really, they deserve my applause because the work that I show you today is only thanks to them. With this, I'd like to thank all of you for your attention.
Thank you so much. Thank you so much. I'm not sure if my mute got hit there as we were going along. That was a wonderful talk. And I think now let's go ahead and bring out our panelists for today. And then we'll also have them ask questions, and we'll also bring forward some questions from the audience. Our first panelist is Dr. Li Tao, who's a young chief professor at Southeast University in Nanjing, where he also serves as the associate dean of the School of Material Science and Engineering. His research includes microsystems and nanoengineering, 2D materials and devices for flexible, wearable, Internet of Things, and healthcare applications. He's won many awards and serves as an associate editor for the Science Partner Journal Research and also for microelectronics engineering. Our next panelist is Professor Zhang Liu. He's a Materials Research Society of Singapore chair professor at Nanyang Technological University in Singapore. His work focuses on synthesis and engineering of large high-quality 2D monolayers such as graphene and transition metal dichalcogenides, physical properties of monolayers such as two-dimensional superconductivity for electricity, for magnetism, and while semi-metals, applications of two-dimensional materials for semiconductor electronics. He's won many, many awards as a good friend and a champion of ACS Nano, which is now based at NTU. And our ex-challenger for today is Zach Martin, a PhD student from Professor Vlad Shalev and Sasha Boltaseva's research groups in the Department of Computer and Electrical Engineering at Purdue University. Welcome. And so let's start with Zach.
Awesome. Thank you, Paul, for the introduction.
And then I'll move on to an audience question. Go ahead.
Okay. Yeah, thank you, Professor Samorì. That was a fantastic talk. Really, really eye-opening, a lot of really cool work. So I kind of am, hopefully I can come up with good challenging questions for you. The first thing I'd like to ask about was this optically switched memory, or these optically sensitive transistor devices that you came up with. So this is really cool, but I noticed in one of your slides, you had sort of a time scale for the switching that was on the order of seconds. And I think you had some sort of lifetime type measurements where you showed that the switching between states is on the order of seconds. So for like electronics applications, is there a niche for second order type switching, or are you looking into ways that you can speed up the transitions between different states of these molecules?
Yeah, that's a great question, actually. So let me put this question in a bigger context. So there are a number of things that I showed today, which actually are based on a project we also developed in parallel using as a semiconductor, organic semiconductor. So I answer to your question based on a knowledge that we have developed in the last 10 years, first with the organic semiconductor combined with the photochromic molecule, and then with the one here in 2D materials. So to address this question, first of all, of course, the speed of the switch is very important, and this already can be modulated by choosing the right photochromic molecule, okay? So generally speaking, therefore, for example, among the 3 different families I showed you, azobenzene, that is the most common one. Actually, if I have to quantify the number of people you can find literature on azobenzene, probably is 90 versus 10, or actually 98 versus 2 compared to diaretin, okay? Of course, the synthesis is much more simple and so on and so forth, but it's a slow switch by definition, actually. For application electronics, actually, diaretin is much better. In a device, we could show, this was already in the first paper we published in 2012, that we have a microsecond time scale response, okay? So that, I think, technologically is interesting. I mean, microsecond is already on a time scale without any kind of optimization. So there is room for expansion, but starting from microsecond, that's okay.
Thank you. Yeah. So how might you? Oh, I'm sorry. Just as a follow-up question, how might you go about improving the time scale from microseconds to, say, hundreds of nanoseconds?
I think here there is 2 things that have to be done in parallel. That is, there is a materials optimization, and there are some tricks that can be used in material synthesis in order to improve let's say the speed. But there is also some kind of device optimization. Now, for what concerns device optimization, despite let's say we fabricate proof of concept device, I also insist that we are not engineers. We have engineers in the group, but it's not our game, the one of, let's say, optimizing the device engineering, okay? So I don't think we are competitive enough. But that is also one of for sure, the optimization has to be carried out in order to improve the speed.
Thank you.
Very good. Before we move along the panel, we have a couple of questions from our audience around the world. And the first one comes from Sinja in Shandong. Thanks, Professor Samorì, for your wonderful talk. I learned a lot. For the doping of 2D materials, you mentioned that there are several approaches and you gave light-based examples. Can you also comment on other methods, particularly magnetic methods, which were in the chart there?
Well, we haven't reported anything about magnetic method yet. There is a lot of room. Well, we are just starting a new European project on that. But of course, I think if you look at what I showed today, you can already have some ideas of how you can play with magnetism. We are exploiting molecules that actually we are not discovering anything new. We are just combining, making hybrid out of molecule whose function was already known. Okay, and we interface that in a controlled fashion with the 2D materials. So I think I provide already kind of an answer to your question. Then at that point, you just have to look back at the literature of molecules with magnetic controllable properties, and then see how you can interface it. And if you don't know how to interface it, our chairman will teach you how to do it. Right?
Oh, thank you very much. Our second question comes from Dr. Xu from the Beijing Institute of Technology. Dear Professor Samorì, as you said, defects are sometimes not a bad thing, but how does one control such defects? There's a big issue for mass production, especially when we want to keep the quality high.
Yeah, of course, that's a major challenge. The first of all is you need to decide if you want defects or not, okay? Because as I said, you don't have to look at defect only as something completely negative, you know. There are a number of applications where you need defects and you need control and defects. There are a number of external stimuli that you can use, and you have to optimize given the type of 2D material that you want to play with in order to create one type of defect and not some others, okay? So that is really where, let's say, a multi-scale analysis is to be done. And then based, again, I think the whole process has to start from what you are looking at, what you're looking for in terms of application and in terms of properties. And then you do the retrosynthesis. So I think it's time for the physical chemist to work like synthetic chemists, to start from the final product and go back. Whereas we have been taught to start from the initial and study the properties. We have to do a retro physical chemistry analysis.
Yeah, in fact, in the monolayers, control of the defects turned out to be a key for our laboratory over the last 25 years. And that is possible, I'm sure. In this case, that'll be developed as well. Well, let's move to our next panelist, Professor Zheng Liu. But we'd like to be able to hear you.
Hello. Hi, Paolo. Thank you for a great talk. Yeah, you are like a magician of the 2D materials to create a lot of things. So I'm just wondering that you have used so many kind of molecules, right? Molecules that can lock the 2D materials. Molecule can supply sulfur to the sulfur vacancy, or molecule for the liquid gating. So I'm wondering, how can you come out with this kind of molecules in terms of the chemical ways? Because I'm physics background, right? It's very challenging for me to find these molecules.
Well, you know, they actually, it really depends on the community you're talking to, because I always had the feeling that when frequently we interact with synthetic chemists, but the type of molecule we play with, from the synthetic point of view, are probably not the most challenging one, you know. So sometimes it's also embarrassing to ask to one collaborator to synthesize a molecule, which after end is something that for the PhD student in this group is not a great challenge, you know. For us, it's already, the point is we need to find the right compromise, because already a simple molecule has some sophisticated functions that are hard to be controlled. So for us, it's already an extreme in terms of function sophistication. For the synthetic chemist, actually, it's the other way around. It's maybe it's too banal. So the molecule we play with, I think, are simple. What we in their design, the control of the properties. This is something that has not been done, in my opinion, fully. And so that is what we spend a lot of time into. And also because once you interface with the 2D materials, then the properties, they diversify a lot, you know, so you just have to sometimes learn something that you would not expect, you know. Now we, of course, for example, on the photochromic molecule, we have built up a knowledge over 20 years, okay? So that was kind of something that we developed step by step. But again, without trying to complicate the structure too much, because of course, then it's also very hard to control the way it interacts. I mean, the main key, and that, of course, is a kind of issue that I share with Paul, because we come from the same community of a lot of microscopy, you know. We want to know the structures. I mean, intrinsically, if we don't know how they, when you create an interface, if you don't know how the two components interact, I'm not happy, because I want to be able to control the structure, first of all. And so the control of the structure already requires quite a lot of study and quite a lot of design of the two components. And then, of course, when you have a control of the structure, you can try to control the properties. I don't think you control the properties if you don't have control of the structure. Okay, so it's a kind of two-step process.
Thank you, Paolo. Yeah, a following question about the interface. As you mentioned a lot of times, right? Interface will dominate the property, the nature of the 2D materials. So according to my understanding, I believe a 2D material is a big molecule. It's really big, right? Sometimes it's single molecule. And the chemical molecules are relatively small. So it will be very important to establish something that we know how they can interact, or the coupling between them. Do you have any idea or experience on this point?
Yeah, that's a good point. First of all, I completely agree with you, but I'm not sure that everyone agrees with us that the 2D materials is a macromolecule, okay?
I agree.
We fully agree on that, but I'm sure that we have a number of people that will disagree, but okay, whatever. Then, of course, that is a very important point, that you have a problem of dimensionality, that there is the 2D materials is huge, is macroscopic, and then you have small molecule. But small molecule, you don't have to look at small molecules as individual objects. Small molecules interact among them, and they assemble into larger objects, okay? And so that allows you to match the dimensionality, okay? And that is actually the trick that we use in order to create this kind of hybrid heterostructure that is inorganic on the bottom, that is a classical 2D materials, and organic on the top, because actually the small pieces of our puzzle or the small pieces of our Lego interact laterally to create an entire 2D materials that is organic. Okay. Then, of course, nowadays you can look at this into non-covalent interaction, but you can also look at the small piece of this puzzle, of the organic puzzle, to interact at the covalent level. So there is the entire world of covalent organic framework, the world of 2D metal organic framework. So I think there is the materials, let's say, library is expanding. That is great. So there is a lot of room to expand to new properties for sure, using this kind of new building blocks.
Okay. Thank you, Paolo. Thank you. Thank you again for the wonderful talk.
Thanks.
Very nice. Thank you. Professor Tao.
Hi. Thanks, Paul, for such a comprehensive talk that is really eye-opening. And I really enjoy the concept of that bridging from the big picture of interdisciplinary approach between the chemistry and the physics in the device, and all the way down to the very specific example you showed about connecting the flakes for better performance. You know, I could ask tons of questions, but for the sake of time, I just go down to one specific point about your latest work at the advanced material using that SAMs to control the dipole moment, playing with the Schottky barrier and manipulate the charge carrier, say electrons' behavior. And I'm just wondering, because typically the device performance is determined not only by the carrier behavior itself, but also like the action, like scattering between the electrons and the phonons. So how those SAMs layer could affect this kind of phonon behavior, or the interaction between the electron and the phonons, and then like change the performance of the entire device. Could you shed some light on that point?
Yeah, that's I think is a great question, which I have no answer, in the sense that that was really a preliminary study that we reported showing the concept that it can be applied. In my opinion, we have now a kind of device architecture to do a lot of in-depth physics, because it's the first time that really you have asymmetry in the injection with eye control over the Ward function. You can add an active tunability. I mean, one has to admit that you need, let's say, an amazing user with great hands to do that. I think that not each student would be able to do that, because it implies a lot of microfabrication, very, very delicate. And at the same time, I'm not sure that we can soon think about using this approach on a large scale, because of course, really it's a very subtle microfabrication, let's say, process, the one we've been developing so far. But on the other hand, all this after about how phonon electricity interacts, as you were raising up, these are very key questions that we need to tackle in the future using this kind of new device architecture. But I have no answer, because we haven't explored that yet.
All right, thank you. It's a very inspiring work. Thanks.
Thank you.
I'll take the opportunity to ask a question. That is, how do you choose the molecules for doping and control on the surfaces? Do you have a strategy for which ones you? Yeah.
Well, first of all, you need to decide how you want them to interact with the 2D materials. So you need to design your experiment and decide if you want to have interaction that are at the physical level, so physisorption or chemisorption. So that already defines the type of anchoring group that you can choose. Then, of course, the wish is to have systems that they have high dipole moment intrinsically. So that then by design, you can play, of course, with fluorinated molecules, or you can play with amino functionalized molecule. You can take the library of molecules that have been already used in the past, like, you know, the typical TCNQ type of dopant. I really believe that one can reutilize the whole library of dopant that have been used, for example, with organic semiconductor. I honestly use very much as a source of inspiration all the work that was done in organic semiconductor, and apply this to the materials in terms of how you control the interface with dielectric, the way you control the interface with electrodes. I mean, organic semiconductors start in the 80s, is not in the 70s. So the materials start 30 years after, right? So, I mean, there are 30 years of knowledge that can be actually exploited, and it's all available. So that is what I would encourage everyone to do. So the, yeah. Well,
if you could design those, oh, go ahead. If you could design those from the bottom up, do you have a set of criteria that you would use?
Yeah, I mean, okay, I must say, in general, I love switches. I love switches because I like to see things that are changing under my eyes, their properties, okay? And they kind of respond to the input that we can provide. So not only because I like this kind of change, but also because if it is a reversible switch, then you can have doping, and the doping, you can really have a kind of controlled experiment under your eyes while you do the experiment, you know? And so that is the reason why we have been always kind of integrating this kind of dopant inside, let's say, the switchable unit. Here today, I gave a lot of emphasis on the, let's say, photochromism, and of course there with the dipole moment, the spiropyramid is the best solution, despite also with the isobanding, there are a number of things one can do in terms of changing the dipole moment in the two state. But I want to stress indeed that beside the magnetic field that was mentioned in the previous question, you can also have other stimuli like, you know, electrochemical stimuli. This is something we reported recently as well. You can use basic building block that has been already demonstrated, like ferrocene based or other type of stimuli that have been pioneered, for example, in Barcelona by Jaume Venciana. These are a number of available, let's say, switches that one can master and integrate into material. Now the question is indeed how you interface them. And I think there is a lot of room. I showed some idea, but I also showed the 5 positions where you can place them. That, of course, as a chemist, Paul, you know that the cartoon is nice, but then to make it happen, it is slightly more complicated, right?
Often interesting to find the differences and illuminating.
Yeah. People love to say, I talk to molecules, they listen to me. Well, my molecule, they listen partially, not fully, you know. It's not so easy, in particular, when you have so many interfaces to decorate in a, let's say, asymmetric fashion, to be able not to interfere one with the other. But I think that is where the chemists have to enter inside this game. I insist that there are too many physicists inside the 2D materials world. There is a lot of room for chemists, so please come and join us.
Well, along those lines, what is it you hope to be able to do over the next decade? What's your big picture goal with these systems?
I think what is one should try to do is to increase the functional complexity and demonstrate, give proof of, let's say, new, let's say, device logics based on the combination of different type of components. So that step by step, again, also there is not an engineering challenge. We're not reinventing a new type of device. We use a well-known architecture and try to provide the added value of integrating molecular functions in there. And so that is where I think given that molecular are stable, are as stable as a normal semiconductor, as this was proven in a number of applications on organic electronics. So the technology can be there. Then, of course, the added value will come from all the portability that you can have and flexibility, foldable, wearable, and so on. And there as well, I think that there is a lot of future in sensing, in both physical and chemical sensing, based on, let's say, molecules combined to two materials, because this somehow, I believe that it is our responsibility to try to tackle some of the society challenge. And let's say the quality of life, health is for sure one among them. And there is a lot that one can do in order to have a point of care kind of device like the one that you nicely showed a couple of months ago. I mean, today, these things are amazing. If we think 20 years ago, you had never thought about having a clock that tells you everything about how you feel, right? And I think we can go towards more and more sophisticated detection of, let's say, signals, chemical or physical, that come from our body. You know, these are portable. They run on whatever, 0.5 volt, which doesn't hurt our body, our way of functioning. And so for sure, this is for the, let's say, health monitoring. Environmental monitoring as well, I think there as well, After all, what we have is a kind of 2D materials that have all surface and no volume. So their properties are so susceptible to the environment that if we are able to give a concrete answer to the question of selectivity in the sensing process, then we have the right type of sensor, of chemical sensor we are looking for, because the sensitivity is there for sure. The selectivity is an issue, but there again, chemistry can do a lot. So that, I think, are a few ways to go.
Fantastic. Well, let's thank our panel. And again, thank you for this really thoughtful and inspiring talk today. You know, I think one of the first trips I had canceled during COVID 2 years ago was to see you in Strasbourg. And so
Yeah.
we'll look forward to the opportunity to meet in person soon as the world reopens. And normally I'd be able to walk across the stage and hand you a plaque to thank you for giving this talk. But in the meantime, you know, we have this electronic version of a certificate, which our host, Professor Alice Zhang, will send over to you shortly. And you know, it's wonderful to connect in this way and to, you know, reach out to the entire world. One advantage we've had over COVID is we have such an attentive audience of tens and hundreds of thousands of people who hear these talks, including some of my first-year undergraduates this morning. And so to them, I'll see them in class in a few hours, and to you, I will look forward to time very soon when we can get together and talk science and look at how to functionalize these materials together. Thank you so much.
Fantastic. Thank you very, very much, Paul and Alice. It was great. Thank you.
Terrific. And we have coming up on the 8th, which will be Tuesday, Women in Science, and Professor Alice Zhang will be hosting that. You can see we have a terrific lineup coming up. And then next Friday, okay, let's stick with the summit. So we have a summit coming up at the end of April with luminaries from around the world, including Nobel laureates Jean-Pierre Sauvage and Stefan Hell, as well as Gang Chen from MIT, our co-host Jagadish, co-host from last year, Jagadish, and a number of other terrific speakers. So stay tuned for that. And then next week, we have a special treat to have Professor Justin Haynes from Johns Hopkins, the head of nanomedicine in their world-leading eye institute. And so stay tuned for that, and we'll look forward to seeing you at that as well as on Tuesday's symposium. Thank you once again from Los Angeles, Beijing, and around the world.